Okay, I want to make clear that you guys completed the assignment successfully. So I posted it after class last Tuesday. So I tried to make clear some points that were asked after class. I think the most important thing is that I don't want you to go down the recursion tree. I'm okay with one step. So up there we start with f. F will have size m, and m will be decomposed in fk and m over k, and that's enough. You can stop at this level. Okay, you don't have to traverse the tree further down. Another question. Let's see if I remember. This was important. There was another one that I wanted to clarify. Yes, the padding. So, some of you are confused because I said pad the input vector, and you were asking what do we do with the rest of the formulas. So maybe I didn't make the padding concept clear. So let's make an example. Let me give you the example very, very clearly. So our input vector is of size 15. Okay. And for some reason, I am not particularly smart, and I ask my 1D FFT of V4. Okay, this is a stupid request. I have to compute the FFT of an object of size 15, and I want to decompose this FFT in pieces of 4. Well, clearly I cannot do that. So what I am suggesting you guys to do is to scratch this, and inside the my1 FFT, what happens is now V becomes V and 0. If you want, we can call this V1. Okay, now V1 magically is divisible by 4. And so inside of this thing now we have a call to my 1D FFT. It doesn't have an explicit call, it's just what it has to do. V1, 4. Okay? So at that point you forget about this V, you don't have it anymore, and you just tackle this problem. So the decomposition formula inherits everything from this. This is clear? Okay. Okay, then I think maybe half of you asked me about these requirements. No matrix of size m times m. Like, oh my God, how can we solve this problem? All of these objects are m by m. And so you are complaining. And I have told you, if you create an m by m matrix, then what do you do with it? You multiply times a vector. And then you would have an n square object matrix times a vector. What's the complexity of that? N squared. And I told you, why are we doing this? Because this brings the complexity down to n log n, which means we do not want to do matrix vector multiplication. Which means, of course, I really mean that you cannot use m by m matrices. Yes, I mean it. I'm serious. And cron, it's the same story. Yeah, the matrix is defined by cron. That doesn't mean that you have to use it. Okay. Clear so far? Now I want you guys to have this clear, because when we go to the 2D FFT, okay, now the things is a little bit different. In 1D FFT, our input is a vector. And so all the matrices are only in the computation part. In my 2D FFT, the input is a matrix. So of course now you can use a matrix, an M by N matrix. That's your input. But that's the only matrix that I want you to use, okay? So be a little bit flexible. Also, same rules, which basically also means you don't need to go down the recursion. I have already decomposed our formula. Notice the formula is exactly the same, and I already applied it with 2. Our k here is 2, and I've already expanded this term. I have already expanded this term for you, so I've been utterly nice. Okay, so you have it. I also want to, I don't think I said this in class. All of these objects, well, I did say that it's symmetric. The matrix, the Fourier matrix is symmetric. It's in one of the slides. What does that mean is that if you transpose it, it's the same as itself. What it means is that you can take all of this formula and you can transpose it, and the formula gives the same result. That's when you are in 2D. Notice that I apply the formula in one form here, and on the other side I have transposed it. That's why there is P transpose. It's not a typo. P is not symmetric. The whole thing is symmetric, not each individual piece. So when you transpose this whole thing, here it comes, and P comes here with the transpose. So it's up to you guys to figure this one out. I added the slides on the 2D FFT. I explained what the 2D FFT is mathematically. Maybe I can repeat it briefly because I put it in the slides, but I didn't show them to you. Yeah. Sweat. Okay, so 2D FFT of a matrix Y, no, of a matrix X, by definition, is FFT on the left and FFT on the right. Of course, X doesn't have to be squared, M times N, so it's going to be an Fm here and Fn here. Okay, this F is the 1D FFT, is the Fourier matrix. So if we look at this, let's go here, we can write X as a collection of columns. Okay, and you can see that this is nothing else than a matrix product, and the matrix product can be written as a sequence of matrix vector products. So and what is this? Fourier transform, 1D Fourier transform of each column. That's here. So we get to an object that is, say, X bar Fn. I have computed the 1D Fourier transform of each column individually, and now I am at this stage. Okay, at this stage I can do, I could either decompose horizontally, or for high performance reason, what you would actually do is you transpose this thing You transpose this object so that this Fn comes on the left. The transposition, it's a symmetric matrix, so you don't really have to transpose it. But X is not symmetric, it's probably not even square, so you do have to transpose it. And now from here, what do? F of n. Now you decompose the transpose in columns, and you compute the 1D FFT of each column of the transpose, which means of each row of the original matrix. You get to X double bar transpose. Unfortunately, now you are in the transposed word, so you have to transpose again to get to the actual 2D FFT. You might wonder why the transposition. Well, this is probably because, and not probably, I'm telling you, because the FFT, the 1D FFT, has been optimized as hell when you apply it in the form of matrix times vector. And if you have a vector times matrix, you would have a penalty. So since you have a routine, an high-performance routine for computing this already, then you would transpose, compute the 1D FFT of the columns, which are the rows of the transpose, and so on. So then in the end, you would have to transpose again. Following this, the same strategy, you can go to 3D FFT. And in fact, ND FFT. Let's look at 3D FFT. What would that be? You have a parallelepipedon, and now you have to compute the FFT of each of the faces. So you would have to compute the FFT from the left, from the right, and also in this third dimension, okay? Which means the F of each rows, the F of each columns, the F of all the beams. But that's nothing more than 1D FFT along one dimension, then you transpose, 1D FFT along another dimension, then you transpose again, 1D FFT of the third dimension, and so on. So you can decompose any n-dimensional FFT as a sequence of n one-dimensional FFTs. This is just to say that you can compute anything in terms of one-dimensional FFT. This is not at all to say that that's the way it should be done. In fact, the performance of this object is terrible, especially when you move to parallel computing. This is the way of not doing it. So what is a better way of doing it, the 2D FFT or 3D FFT? What I'm forcing you to do as an assignment. Okay, this is a way of computing a 2D FFT, decomposing the problem recursively without actually going down in dimension. I think that's enough for this. Questions? Has anybody tried this yet? Yes?
I don't have a question.
Oh, you were just waving at me?
No.
Hi. You did.
I asked if anybody had tried it yet.
Oh.
People started to wave.
I see. Good. So, we're good with this? Third part. So I changed slightly the requirement. I told you that I wanted you guys to submit 3 files. Actually, I changed my mind and I added a drop.pdf, so that's a 4th file. What do I want in the drop.pdf? Okay, I want you guys to experiment with different values of k. So I want you to show when basically an image starts losing quality. So, and then you can create a PDF document. I put down here how to read an image, how to play with these things. So I hope that now everything is clear. Something that I don't, yes. If you remember the presentation, the demo, I was doing FFT shift, then I was doing some manipulation in the frequency domain, then inverse FFT shift, inverse FFT. And here I forgot to write compute the inverse to the FFT, and I forgot to put inverse shift first and then compute the inverse to the FFT. So please pay attention to that. But you know, if you have looked at the lecture, it should come naturally. I had an interesting question on about the FFT shift. Unfortunately, I wasn't able to answer. If you guys become expert on the use of FFT shifts, I'm interested to learn about it. All right, questions? Yes.
What do you want to draw PDF?
I say experiment and show results for different values of k. Now, in my web page, I realized I made a mistake. I put up 3 images. Each image is like 1.5 megabytes. So I realized if you start experimenting with different values of k and you send me, I don't know, 4 or 6 images, my mailbox is going to blow up. So maybe I will remove these images and just use something that you like. And make it small, please, okay? Okay. MATLAB is over, and on Tuesday we start with Mathematica. This doesn't mean that you need to have Mathematica running. This will take a number of lectures. As I said, I took Python out of the script, which means that we have spent a little bit more time on MATLAB. We will definitely spend considerable amount of time in Mathematica. So from Tuesday on, we do symbolic computations and functional programming. See you on Tuesday.